Hello everyone, my name is Zeng Guowei. Yeah. I already worked in Baidu DBA group for 7 years. Now responsible for the infrastructure of database management. So today I will introduce the Baidu high availability solution for large-scale database systems. This is the agenda of this topic. Firstly, I will introduce some backgrounds of the MySQL at Baidu and the HA tables we made. And then we will analyze some current HA solutions. After that, we introduce ours. At last, I'd like to share some benefits and 2 online cases to all of you. So MySQL is one of the most popular open source relationship database, right, in the world. In Baidu, over 95% of online transaction processing business using MySQL. The important such as search engine, the advertisement, the financial, and so on. Baidu DBA groups manage all of the online MySQLs, more than 1,000 clusters, 2,800 slices, and 13,000 MySQLs. Then they stored PB scale data and carry over 100 billion queries each day. And we also output our service to the cloud. This is the right one is the Baidu's MySQL architecture. The application accesses the MySQL storage through the proxy layer, and the proxy layer can do the write and read separation, load balance, and sharding. As we know that different from the stateless of the application modules, MySQL is a stateful service with data. The write requests are processed by a single MySQL node, right? So if the master is not allowed to write, it will affect the application's continuity. What's more, the data consistency is also very important for the OLTP services. Most of them are not allowed data losing. So what the challenges we met in Baidu when using MySQL? We had mass clusters cover the core business. So the HA solution needs to be accurate enough. And the database deployed in over 10 data centers and multiple regions. So the HA solution should be able to support the concurrency recovery if the IDC or data center failed. What's more, as our business developed, our MySQL online version is so many, so it makes our HA solutions more capacity. Of course, if manual guarantee the recovery is uncontrolled, it depends on the skill level of DBS, so it should practice regularly. When the fault occurs at 3 a.m., we should get up, open the computer, maybe a cup of coffee, and then recovery. 10 minutes left, I think. What's more, when more than one cluster fails, we hope we have so many hands to handle it. So the automatic HA solution is inevitable. It includes 3 points: HA concurrency, the failure detection, the accuracy should be as high as possible because the switchover is lossy. The failure will cause the manual intervention, eventually enhance the service recovery, the recovery time, and the recovery. The data consistency is very important in the recovery time. So next, we will introduce how we solve it. Currently, the most popular HA solutions are MHA and MMM. Both of them have some weakness. On the architecture, the manager is a single node. it is a risk for the fault tolerance and not support the data center fault. The concurrency is also limited to the centralized architecture. On the failure detection, they just ping the port or send the simple queries like select one. This may lead to the misjudgment, the overload fault, or ignore some hardware fault. And it is so difficult to distinguish the dead and the freezing. On the recovery, MHA has a relative complete solution to ensure the data consistency, but incorrect on the earlier MySQL version. What's more, they just use the dump SQL file and transmit to other slabs to execute. So it needs a trust relation build, right, for the machine. But in Baidu, we know we have over 10,000 machines. So it's hard to manage this trust relation. And what's more, we also provide our clouds to the financial institution. It is on safety. It's not permitted for them to make the machine trust building. So how did we resort to meet the Baidu's needs? This is the architecture of our HA solution. It includes two main modules, X-Agent and Config Center. The X-Agent are deployed at each machine. It monitors the MySQL and the machine status. For each cluster, the agent will elect a leader with the help of the zookeeper, and the leader dominates the whole detection and recovery. The config center is used to store the topology configures loaded by the deprocess. And the config center also can make sure the config consistency. The architecture is a decentralized architecture. Any agent that doesn't affect the system, which could make the disaster tolerance, including the machine, the data center, and the region. And this architecture, it also has a good scalability. It is easy to deploy and can cover over 5,000 MySQLs. As we previously mentioned, currently most solutions detect master failure just by pinging the master's listening port or queries. There will be some misjudgments. We could analyze the following case. Case one, the overload. When the query of the application increased suddenly, exceeds the capacity of MySQL, in this situation, ping the MySQL port is okay. But there has two things. Seems A, connect the MySQL maybe is okay, but query is timeout. Sim B, connect error because no resource to respond this connection, right? The simple detection maybe misjudge this case as fault. For the case two, we can take the disk failure. There has three things. It's more comfortable, I think. When you ping the machine, is okay, but when you connect it, it's also okay, right? Because the connection is okay. It's just the MySQL is alive. It's just a disk failure. It can't handle the write. So we can see the first thing, the connection okay and read okay. So it may miss this failure, right? The most badly thing is that the last two things. It nearly looks like the overload, right? So the system needs to distinguish the overload and the disk failure at this time. Okay, let's see the third case, the machine freezing. I'm not sure whether you made that, because in Baidu, when most machine down is just freezing, not really down. You ping the machine port is okay. You ping the MySQL port is also okay. but it just can't work. So at this time, when we ping MySQL, ping the port is okay, but we connect failed. This thing is just a little like the overload, right? So it also need to distinguish at this time. What's more, at this time, the agent is dead. The local machine agent is dead. So you can't detect by the local machine, by the local agent. So what's the badly thing is that at this time, the slave status is also okay because their IO running is yes. The thread is suspended. So how can we distinguish this failure at this time? Okay, so look at what's our solution. Look at the left table. We classify the failure into 3 types: instance failure, machine failure, and network failure. The instance failure and the machine disk failure could be detected by the local agent, which we call the instance detection. The agent reports the key status of MySQL and the machine to the leader. When the instance detection judges the master is done, or the agent didn't report the status to the leader, for example, like the machine dead or the machine freezing, so we will go into the cluster detection. The leader will request other slaves to return the replication information to judge the master status. When make sure the master failure, the leader will start the global detection, because sometimes like the net jitter or the master dead repeatedly, at this time we don't want to recover, because we covered and it's down again, cover and down again. At last, no instance can use. So at this time, at the global detection, we will check the recovery interval, or sometimes we will check the capacity after recovery, because the capacity may be not enough. Or we will also check the expectation of the manual invention. Okay, here are some cases of the master failure detection. In the instance detection, X agent could judge the MySQL dead or freezing by connecting it and check the error info. If too many connections, it may be overload. So write a disk file to eliminate the disk fault. In the cluster detection, the leader checks all slave status. If all slaves are no, we can make sure that the master is abnormal. If status is yes, maybe it's just the X agent dead, right? Therefore, there is another case, machine freezing, which the slaves is still keep the replication connection. So we could let the slave reconnect the master with the replication user. Again, if failed means that the master's machine is freezing. In the global detection, we will check the last recovery time to judge if the repeated forcing. If over the switchover interval, it may be because the net jitter or repeated dead. This will report to the DBS and waiting for the next comments. Okay, the recovery, during the recovery periods, the master recovery includes 3 periods, right? Firstly, try to keep at least the slave's data consistent with the master, and then fulfill the data between the slaves. At last, it will elect the new master by some strategy, like the weight or the data center or something else. So in the 4th recovery period, the most important is to make the data consistency. Next, I will focus on this. The data consistency between master and slave, in fact, it depends on the replication solution. Now, there are three populars. The traditional is async. Master returns the result if it writes success. The slave retrieves data from master with binary log asynchronously. When the master fault, we will try to recover the data from the master's binary log, but it's unavailable if the master's machine dead. So it may be lost data, but this is suitable for the high concurrency and low response scenes, like the forum business, the research links business. To fix the sync's weakness, the semi-sync or group semi-sync solution makes sure at least one self gets the binary log, so the slave's data is able to consist with the master. This solution will lengthen the response time. It always used as a financial or commercial business. These years, we also patched the raft on the binary logs delivery, and the official MySQL version also released MJAR. This solution needs at least half of the slaves received logs. It will make better data consistency, but it will make the response time longer. And what's more, it may make the switch over more sensitive. So we are still exploring this in Baidu. We can choose, in the applications, we can choose one depends on the application needs, in fact. Okay, to fill the data gap between the slaves, there are standard steps I write here. Firstly, all the slaves report the data progress to the leader, and leader compares them and ensures the slave with complete data. We call this slave tinker node. Then the leader will wait for all slaves to execute the local real logs if delayed. Step 3, ask the tinker to find all slaves' sync position to fulfill the gap data. Currently, the MHA finds the sync position in tinker using real logs. Then dump the MySQL file from the real logs from the tinker to the other slaves to execute. So here are some problems for this method. First, the early MySQL version, the binary log event position is not correct. So at this time, if we use the position, it will mess up the data. Then second, what's more, on the step 1, we need to wait all slaves finish the payback of all real logs. If one slave has a huge delay, all slaves will wait for this node. So I think we can make, is there any better methods for this performance? And the third, the SQL file transition needs to build the machine trust relation. I've already talked. So this is on safety for us. So what's our method? We use the timestamp mechanism. We replace into the master's heartbeat table with timestamp regularly. The data progress can be represented as a tuple. The last timestamp and the offset. The offset is the last time, is the gap, is the event number from the last timestamp to the end of the relay log. So the leader can easily judge which slave is tinker by the tuple, the timestamp and offset. After find the tinker node, how do other slaves to fulfill the data? For example, here we assume that 3 slaves, slave 1, 2, 3, and the tinker we already choose is slave 1. Step 1, the leader will wait for the tinker execute all logs to make sure that it has all of the data. Then we'll ask other slaves to stop playback and return the data events executed. Here mentioned that we avoid to wait all slaves to playback. Just the leader playback is okay. So step 3, the tinker will find the relative position of other slaves by scanning its real log once. In MySQL, it's not allowed to change master to slave's real log directly. So to avoid dump the MySQL file at delivery, Here we use a trick. For example, the slave tools relation data sync is in for example, the slave two's relative data sync position is in reallog 1, and the slave 3's is in reallog 2. We will flash the binary log 3 times on Tinker to get empty bin log 6 to 8. Then back the 6 and the 7 and link to the reallog 1 and 2. So other slaves can change master to the bin log of the Tinker and fill the gaps. Attention that after the slaves change master to Tinker, in fact, at this time, if the Tinker can be the master, or if it has higher weight, at this time the service is already recovered. At this time, it can serve to the business. Okay. Our HA system had already run online for over 5 years and covered all MySQL Online in Baidu, support MySQL version from 5.0 to 5.7. It handled over 3,000 times fault recovery, and the mean time to restoration is less than 15 seconds. What's more, it recovers more than 10 times really data center failure and nearly 106 simulative data center failure. The service can recover in 5 minutes. At the same time, our HA solution supports the Baidu financial cloud to the market, including the AI Bank, or systems using the MySQL on x86 architecture. Is the first bank using MySQL to support the core trading systems in China. China UMS, the top 1 acquirer in Asia Pacific. What's more, the architecture is also can used for other master-slave replication systems like Redis. At last, I would like to introduce some experience of 2 Baidu applications. The first one is Baidu Personal Cloud Storage. It's the largest in China now, and is also the largest MySQL clusters in Baidu. As the query time is preferred than the data consistency, we use the async replication in multi-data centers. Here we show the recovery time for the concurrency fault recovery. When any center fault, the service could be recovered less in 5 minutes. The second is a financial application with a self-developed distributed transaction database based on MySQL. Because the strict data consistency needs, it uses the semi-sync replication. In the HA solution, we plug in the customized strategies, like handle the suspend transactions. This will lessen the time, so we also static the recovery time online. It could be recovered in 5 minutes for 8 slices. And we keep on to optimize it. Okay, I'll make a summary for today's topic. We mainly introduced the complete and automatic HA solution for large-scale database systems in Baidu, including 3 points. The decentralized architecture, which is easy to manage and high scalability. The 3 layers failure detection, instance, cluster, and global detection to judge the fault scenarios accurately. And then the fault recovery to preserving the data consistency to support multi-MySQL official versions. I hope this topic could give you some experience and lighting for the high availability of the distributed systems. Thank you.